Hello everyone, I hope you are doing well. So in today's video, I'm actually going to go through the 2023 physics exam, for the Northern Hemisphere multiple choice section. So there hasn't been any answers, and some of my physics students have been telling me to go through this paper. Yeah, because VCAR hasn't released the solution. So these are my suggested solutions. So yeah, let's get ready to finish this video. Okay. Which of the following diagrams best represents the magnetic field lines between two magnets? Okay, let's look at A. Absolutely wrong. Remember, north, the arrows come out, and in south, they come in. But here it's saying that south comes out. Absolutely wrong. What about B? Well, absolutely wrong. Two south poles repel each other. Remember, like poles repel each other. So B is wrong. Let's look at C. Okay, so we can see that the north south, okay, it's coming out. The field lines are coming out, perfect. And in the south pole, they are coming in. This one looks good. What about, even this one looks good. What about this one? This one, absolutely wrong. Remember, north pole, they come out. But here, they're coming towards the north pole. And yeah, so he is wrong. So only the possible answer could be C. Perfect. Question 2. Consider the diagram below. Which of the following stationary object shows a stationary object with a field lines that extend outwards from the object? The field line shown is most likely to be identified as an example of... Alright, this can only be an electrical field. And why is that? Well, here it's telling us gravitational fields. No, gravitational fields only attract inwards. So absolutely not. So it can only be... electrical field. So we can cancel D and C. It says an electrical field line that is uniform or non-uniform. Okay, think of it like this when uniform and non-uniform. If we put an object here, if we really put an object right over here, next to the charge, well, it's going to be very attracted. Well, it's really like, the field line here, the field is very strong because it's near the source. And what about if I put the object over here? Or like, let's say on the arrow. Well, what's the difference between its electrical strength, like the strength of the electrical strength? Well, here it will be very strong, and here it will be very weak. So because they are very different, then it is a non-uniform. Uniform means they are the same. So if you put an object over here, they should have the same electrical strength. Absolutely, that's false. So yeah, the only possible answer for this one should be an electrical field that is non-uniform. Yeah, perfect. Two identical satellites, S1 and S2, each of mass m, are placed into two circular orbits around the Earth. Satellite S1 has an orbital radius of 5r. Satellite S2 has an orbital radius of r1, or just r. Which of the following best gives the gravitational force exerted on S1 by Earth and the gravitational force exerted on S2 by Earth? Okay, so I'm just going to put a division here. Okay, now we know that force, so F, force of gravity is equal to what? G. M is the mass of the Earth, and M is the small of the satellite. Because they have the same mass, I'm just going to put it as M over. So this one's S1. So S1 is placed 5r squared. So that'll be 25r squared. Yep. So this ratio divided by, again, G, M, M, because they have this, because remember, M is your mass of the Earth, and this M over here is the mass of the satellite, and they both have the same mass, all over r squared. So just r squared. What can we know? Well, what's then G, M, M over 25r squared times r squared over G, M, M. Well, these cancel out. These r's cancel out. So we only get 1 over 25. So choose A as your answer. Which of the following statements about polarization of waves is correct? Now, you should know that only one kind of wave that gets, polarized, and that's transverse waves. That's the only thing that you should know in this study design. So it says transverse waves can be polarized. Absolutely true. Longitudinal waves can be polarized. No. Both longitudinal and transverse waves can be polarized. Nope. Neither. Nope. So only A is your answer. Yeah. So in this study design, you just need to know that only transverse waves can be polarized. Question 5. The diagram below shows an ideal transformer in which the primary coil is connected to a battery and a switch. An ammeter is connected to a secondary coil. Okay. Which of the following is closed? So when the switch is closed, the pointer of the ammeter momentarily deflects. How could the deflection of the ammeter be made larger? So if we want the deflection of this ammeter to be larger, we need a higher current. Remember, a higher current. And so what? So it says, okay, they're all dealing with, okay. So let's look at this. So this is what we call primary coil. Let's call it N1 and secondary coil N2. And what do we know the ratio between current and, so this is I2 here and this is I1. This is your current in your primary and secondary. And what we want is to have a very high secondary current. And you should know the ratio between the number of loops and the current. So we know that N1 over N2 is equal to I2 over I1. So they are inversely proportional pretty much. So if we want to have a high I2, so a current, secondary coil current, we need to make sure we increase N1 and we need to decrease N2. So it means that your primary coil, we want to increase, and your secondary, we want to decrease. Okay, let's have a look at the answers. So decrease the number of primary coils. Nope, we want to increase that. Decrease the number of secondary coil. Yes, perfect. So increase the number of secondary coil. Nope. Place a resistor in series with the ammeter. No, it pretty much, if you're going to put a resistor, it just, it pretty much doesn't do anything. Because the ammeter or the current doesn't change, so it's quite useless. So only B is your answer for this one. Decrease the number of secondary coils. Is that right? Perfect. An RMS current of 15.6 amps is equivalent to the peak-to-peak current of what? Okay, very easy. So you should know that to get the peak-to-peak current, so 15.6, we must multiply by 2 root 2 to get peak-to-peak current from RMS. I'm doing that on a calculator. That's 44.1 amps peak to peak. And that's C as your answer. Okay, question 7. Electrical generators may use slip rings or split ring commutators when generating electricity. When operating at equal frequencies, the output voltage of these two types of generators can be displayed together on an oscilloscope. The output of the split ring commutator is displayed in a dotted line. Straight away, dotted line. What do we know if we put a split ring commutator? What it does is it reverses, or pretty much this is how it would look. Because it says dotted, it should be above the pretty much the t-axis. Pretty much it has to be above. The output of the split ring is displayed in solid lines, and we know if it's a split ring, it's a normal sinusoidal wave. Which of the following which of the following diagrams best represents these two outputs? Yeah, only C looks like the best one. We can see that, yep, this one is being like this, and where this one is being sinusoidal. Perfect. And yeah, that's that. 8. Saturn has 83 moons. One of them, this, has a mass of this and a circular orbit of radius this. The mass of Saturn is this. Which of the following is closer to the gravitational force of attraction between Euclideus and Saturn? So, force of gravity is equal to G and times the mass of the actual Saturn, which is 5.68 times 10 to the power of 26. Let me just bring this over here, all of this. Multiplied by the mass of the moon, which is 1.08 times 10 to the power of 20, all divided by r squared, the radius of orbit, which is 2.38 times 10 to the power of 8 squared. Let me just do this in the calculator. 5.68 times the power of this times 1.08 times the power of 20. 2.38 times 10 to the power of 8 squared. And that gives us 7.2 times 10 to the negative 19. So D is your answer for that one. So use the following information to answer 9 and 10. Okay. The diagram below shows two stationary trolleys on a smooth surface with an ideal spring compressed between them. Trolley A has a mass of 1.0 kilograms. So this one has 1 kilogram and trolley B has 2.5. Okay. The spring is released and the trolley moves off in the opposite directions. The spring falls straight down. In the first experiment, trolley A moves to the left. So trolley A moves to the left at 0.8. So we'll put negative 0.8 because it's moving in the opposite direction. Let's take right to be positive and left to be negative. So negative 0.8 meters per second. Which of the following is closest to the speed of the trolley B? Okay, what do we know? Well, here is a question that deals with conservation of momentum. We know that momentum is conserved, so we can say that, let's say this is M1 is trolley A, V1 is the velocity, is equal to negative M2 V2. Why did I put that negative? Because they are moving in the opposite. Well, this one is going to the right, this one's going to be going to the left. So I'm just going to put that as that. Okay, now, so what is this mass of the first one, which is just 1? What's the velocity? It's negative 0.8 is equal to negative the mass of the second, which is 2.5, V2, which, yeah, now let's calculate V2. So that we're saying negative 0.8 divided by 2.5, negative 2.5, and gives us 0.32. Choose A as your answer. Yeah, perfect. The experiment is repeated with a different spring. The spring is compressed 2.8 centimeters and is released. Now trolley A moves to the left at 1 meters per second and trolley B moves to the right at this. Which of the following is closest to the spring constant of the spring? Okay, now we should know this is energy conservation. Now we're dealing with energy conservation. So what do we know? Well, think of it like this. Well, the spring, it was compressed, and these are the trolley. So this is trolley A, and so this is the 2.5, and this is 1. Here, because the spring was so compressed, the spring's compressed, all of its energy, and these are all stationary, by the way. This one over here and this one were both stationary. So what do we know? The kinetic energy, so EK, both of them are 0. So all of the energy was coming from the spring, and that energy, we call it strain energy or spring elastic energy. And because of that string, so all that energy was held in that spring. And when they released, the spring pretty much comes back to its original shape, and these ones move outwards. Oops, let me bring this up a little bit. Yeah. These come outwards. Okay, so it means what happened to the energy? Well, this now becomes 0 because now it's not compressed. There is no energy, elastic energy. So what happens to that energy? Because we know energy is always conserved, the energy actually went towards these both trolleys. And now these have kinetic energy. So what do we know? This is what we actually need to look to make a formula. So originally all the energy was in strain energy. So let's write E elastic. So let's say ES. So elastic energy, ES strain energy. It should equal to both of these together. So the kinetic energy of 1 plus the kinetic energy of 2. Okay, perfect. And we know that the formula for the elastic energy is half K, change it in X squared, is equal to the kinetic energy of the first trolley, which is half mv squared, plus half m2v squared. Done. Now we've made this nice formula, and let's now put these values in there. So half K is what we're trying to calculate, and change in X is how much it's compressed. Well, it was compressed by 2.8 times 10 to the negative 2 squared, equals half, what's the mass of the first trolley, which is 1, and the velocity is negative 1.0 squared, plus half, what's the mass of the second one? It was 2.5. and 0.4 squared. Perfect. Now, so let me just calculate these. So 0.5 times 2.8, so 0.5 times 2.8 times 10 negative 2 squared. So this one is 0.000392 K equals 0.5 times 1 squared 0.5 2.5 0.4 squared, and this is 0.7, so therefore K is equal to 0.000392. 1785.7 yeah, so units per meter. So which one would that look? The closest is C. Perfect. Which of the following best describes a hypothesis? An explanation that is correct. So an explanation that's correct, no, that's a fact, I believe so. A statement that is widely accepted by physicists, I don't know. No, that's, yeah, and a hypothesis is what you're trying to, like, when you're making an experiment, you make a prediction. You're like, this is, by this theory, this is what I predict what would happen. So a statement that is widely accepted by physicists, absolutely not. An explanation that has been widely supported by experimental evidence, no. No, you haven't even experimented on it. It's what you want to experiment on. A possible explanation that needs to be widely tested by experimental evidence, absolutely, that's the best one. It's an explanation that needs to be tested by experimental evidence. Perfect. Sophia is moving the end of a slinky spring up and down, creating a transverse wave. Which of the following, labeled with arrows, best represents the amplitude of the wave? Okay, well, just think of the waves. If you do methods, you should know that the amplitude is from here to here. So it's A, actually. And yeah, so A is the amplitude. So you choose A. B, if you're wondering, B is actually, because it's next to peak, it's your period. This over here is your period. And yeah, perfect. So B is your period, A is actually your amplitude. And yeah, that's that. Perfect. A ray of monochromatic laser light travels through air, straight through a glass block of refractive index 1.5. So this is 1.5. As shown, and we know that n is equal to 1 here, of air. Which of the following best describes what happens to the speed, the wavelength, and the frequency of light rays when it's traveling through glass blocks compared to when it's traveling through air? Now, I'm going to give you this hint. Every student should know this. When light is traveling through different n values, or, you know, yeah, when it's traveling through different refractive indexes, the frequency is constant. It never changes. That's what you should always know. Be careful. They will try to trick you. They'll say frequency changes. No, frequency does not change. So let's just have a look at the frequency table. Here it says decrease. Absolutely wrong. Just take that off. Okay, let's literally look at this. Now, if we're going through air, let's say, for example, a light's going through air and it's going through a higher value of n. What happens? Well, its speed decreases because it's like it's going through a thick particle. Like it's going through a thick, imagine like light's going through air and then it goes through something that's thick. So the actual velocity decreases. So speed decreases. So D is wrong. And what's that with wavelength? Well, okay, let's really look at so what happens to the wavelength? Let's see. Well, if velocity is equal to f wavelength, and that frequency is constant, so let's just make it 1. So it's just v. Actually, just yeah, let's keep it f there. And we know that the wavelength is inversely proportional to the velocity. Yes. Oh no, what am I doing? It's velocity over f. Wait, what am I doing? Oh my god. Okay. Yeah. It's wavelength over velocity over f. Yeah? So what is happening? Because f is constant, we can say it's 1, so it's just wavelength is actually equal to your velocity, in other words. So if the speed decreases, the wavelength also should decrease. That's what's saying, so B is your only answer. I hope that's right. Is that a good explanation? Yeah, because we said f is constant, so let's say it was 1, so f v is equal to your wavelength. So We know that speed decreases, so the wavelength should also decrease. Yeah, should be right. Let's move on to the next question. Question 14. A standing wave is produced on a flexible string, as shown in the diagram below. The diagram shows the wave at two different times. The solid line represents what the wave looks like in a particular time, and the dotted line represents what the wave looks like exactly half of a cycle. Which of the following is closer to the wavelength of the standing waves? Okay, because these are close at two ends, you should know the formula for this. It's a very easy formula, and the formula is, if I just have a look, there we go. We know that the wavelength is equal to 2ln, where the L is the length of the thing, which is 5, and n is how many of these kind of circles. This is what so number these, so that's 1, 2, 3, 4, 5. Cancel those two out. There is 2 meters of wavelength, so choose D as your answer. Perfect. 15. Violet light shines on a metal surface and electrons are emitted. The maximum kinetic energy of the electrons emitted is measured to be this. The energy when expressed in joules is what? Okay, so it's easy. So 0.120 times 1.6 times 10 to the negative 19, which is times 1.6 times to the negative 19, which is 1.92 times 10 to the negative 20. So choose B as your answer. What about a proton of mass? A proton of mass 1.67 times 10 to the negative 27 kilograms is accelerated until its de Broglie wavelength is this. The speed of the proton is then closest to what? Okay, so let's look at the formulas. Okay, well, we know that momentum is equal to mv, yeah? So we're dealing with speed. And we also know that momentum is equal to h over wavelength. And so we can say that mv is h over wavelength. And we can say we want the velocity, so it will be velocity is equal to h over your wavelength times your mass. Okay, done. Now putting those values in this equation, we should get the velocity. So your wavelength, so your de Broglie, okay, so let's 6.63 times 10 to the negative 34 all over your wavelength, so which is 5.0 times 10 to the negative 9 times your mass, which is just 1.67 times 10 to the negative 27. So that is times 1.67 times 10 to the negative 27. That is 49.4. Choose C as your answer. Which of the following light sources produce a full continuous spectrum of visible light? Now you should know a full spectrum. There's only one that actually just comes to mind, and that's what we call an incandescent globe, because, yeah, let's have a look at the answers. Well, a laser, look at this. A laser only produces one certain wavelength. It will produce only like a one certain wavelength, so absolutely not A. An infrared heat lamp? No, infrared. It's creating infrared, and we want visible light? Absolutely not. Incandescent globe? Yes, that creates a continuous. Remember, an incandescent globe, think of it like that. That's not a good, yeah. It just creates different everything. It creates every, wavelength of light in the visible spectrum. A mercury vapor lamp? No. Only, yeah, incandescent is the best answer to put, yeah. Perfect. Light of wavelength 300 nanometers is just able to cause the photoelectrical emission of electrons from a lead surface. So it's just able to cause it. What does that mean? Well, this therefore is your threshold. Well, threshold wavelength is just able to cause the photoelectrical emission of photoelectrons from a lead surface. If light twice this wavelength were incident on a lead surface, what would happen? Okay, let's just really look at this. So we're originally starting with a wavelength of 300, yeah? And we've doubled it. So what happens to the frequency? Let's really look at the frequency. Okay, this over here is your actual, what we call is the threshold. So the next value here, what happens to the frequency? Let's say the frequency is, let's say it's 1. Let's say it's 1 originally. And we know that the wavelength is inversely proportional to the frequency. So if we doubled the wavelength, the frequency halves. Yes. So if it halves, then there would be no, because we've gone below the threshold. If it was 1, it's the actual threshold frequency, and we go below the actual threshold, which we've just done right now, then there would be no photoelectrical emission would occur. Absolutely, A is the only possible answer because we've gone below the threshold. So there's actually no photoelectrical emissions occurring now. So A could be the only answer for that one. Yeah. A light of just able to cause the photoelectric from a lit surface if light is towards the wavelength we incident on the lit surface. Yeah. Half of as many electrons would be injected. No, there would be no electrons injected. At the same number, nope. The same number, no. So only A would be the possible answer for that. Some of the energy levels for an unknown atom are shown in the diagram below. Which of the following lines labeled X, EV, these energy levels are not drawn to scale? A part of the emission spectrum of the atom shown in lines at 1, 1.6, 1.9, the value of X is closest to what? Okay, so let's just have a look at what are the emission spectrums that's happening. That are related to the X. Just remember, we don't want to write all of them. So, well, we've got one that emits from here to, so X to 0. We also have one that emits to here. We also have another one that emits to X. We also have this one that emits to X also. Is there anything else we also have this one that emits to over here. And yeah, like these are the only ones that we want to deal with. And I'll be honest, if I was in the exam, I'll do a guess and check here. Let's try 7.7. Let's put this value here, 7.7 it means. Let's check. So 10.4 minus 7.7. This is 2.7. No, it's none of these in none of these. So absolutely not. So what's 9.5 minus 7.7? 1.8. No. So this one's 1. So we're saying this is 1.8 here. That's still wrong. It's not part. 7.7 minus 6.9. 0.8. Nope. And yeah, so it's not A. What about B? If we sub 7.9 over here now. Let's check. So what's 10.4 minus 7.9? That's 2.5. Nope. 9.5 minus 7.9. 1.6. Okay. We get 1.6 over here, which is one of these. That's good. 7.9 minus 6.9. 1. Okay, that's good. We also get 1. We're also getting 1. Then what's 7.9 minus 6.9? We get, okay, that was 1. Then what's 7.9 minus 7.9 minus 5.1? 5.1, no. So, yeah, so if I'm not mistaken, so 9.5 minus 7.9. So it could not be B, because we did not get what we wanted from here. What about 8? So we're saying 10.4 minus 7. Not 7. We're now changing that value to 8. Minus 8. 2.4, nope. 9.5 minus 8. So 9.5 minus 8. That's 1.5, nope. 8 minus 6.9. That's 1.1, nope. Yeah, it's not 8. Let's try C. 8.5. So 10.4 minus 8.5, 1.9. Okay, we get the 1.9 that we want. 9.5 minus 8.5, 1. Okay, we also get 1, that's good. 8.5 minus 6.9. We get 1.6. We get all of them. So choose D as your answer. Yeah, I would just do trial and error for this one, I'll be honest. Yeah, should choose G as your answer. Last question. A pion and its antiparticle, each at rest, annihilate and produce only 2 photons with a total energy of this. The masses of the pion and its antiparticle are the same. The rest mass of the pion is close to what? Okay, so we EMC squared, and our energy is 4.5 times 10 to the negative 11. M, and our C value is what? 3.0 times 10 to the power of 8 squared. So our M value, our mass, is 4.5 times 10 to the negative 11 over 3.0 times 10 to the power of 8 squared. That will give us 5 times 10 to the negative 28. Be careful. It says that's the mass of both the pion and its antiparticle. But because we know that they're the same, we only want pion, we must divide it by 2 just to get the actual pion itself. So divide that by 2. That gives us 2.5 times 10 to the negative 28. So choose B as your answer. Yeah, it's not a bad exam. A typical exam like always. But yeah, it's not too bad. Question 19 was alright. Just had to guess and check. That's the best possible answer. You should never do algebra, especially it's a multiple choice question. And yeah, this exam was not too bad. I hope I got them all right. Yeah, because there hasn't been any suggested solutions. Like there hasn't been solutions released by VCAR. So yeah, hope you can pretty much check your answers while doing this exam. Yeah, just have a look at mine and compare them. Hope you guys have a good day and take care of yourselves. Bye bye.